Differential equation solution types. We've already learned how to solve linear homogeneous differential equations with constant coefficients. We know what we do is we write the auxiliary equation for the differential equation and say the form of this equation is P of m equals 0, where P of m is a polynomial, nth degree polynomial corresponding to nth order differential equation. And then we find the roots of P of m, the m's, and then we form this general solution to the differential equation by using the m's, the roots of P of m. And a very simple case of doing this is the second order linear homogeneous differential equation with constant coefficients. Now it has this form. We have a sub 2 times y double prime plus a sub 1 times y prime plus a sub 0 times y is equal to 0. Now this is the differential equation. Now a0, a1, and a2 are constants, and a sub 2 is not 0. Now we know that the auxiliary equation for this differential equation is the equation a sub 2 m squared plus a sub 1 m plus a naught equals 0. If we were to use the quadratic formula to solve this auxiliary equation, we would get m is negative a1 plus or minus the square root of a1 squared minus 4 times a2 times a sub 0 all over 2 times a sub 2. And the expression under the radical, the a1 squared minus 4a2 times a sub 0, is called the discriminant. And the types of m's that we get will be determined by the sign of the discriminant. We have three possibilities, three possible outcomes. Say case 1. Suppose the discriminant, a1 squared minus 4a2 times a sub 0 is less than 0. Then, since the square root of a negative number is a non-real number, and we get one solution using the plus, one solution using the minus, we see that our m's will be complex conjugates. And we know the form of the solution of the differential equation that we get when that happens. Okay, so we have complex conjugates. M's. And we know when that happens, the general solution to the differential equation has the form y equals e to the ax times c1 cosine bx plus c2 sine of bx, where the complex conjugate solutions are m equals a plus or minus bi. Now the second possibility, let's say, is that the discriminant is exactly equal to 0. So a1 squared minus 4a2 times a naught is equal to 0. Well, then we get one real solution to to the auxiliary equation. So we have the case where we have a repeated real root. And we know what happens in this situation. The differential equation solution, the general solution of the differential equation, will have the form y equals c1 e to the mx plus c2x e to the mx. Now, case 3 is where the discriminant a1 squared minus 4a2a naught is greater than 0. Now, in this case, we get two real m's, two distinct real m's. And we know that when that happens, the general form of the solution is c1 e to the m1x plus c2 e to the m2x, where m1 and m2 are distinct real roots, or real solutions to the auxiliary equation. So we see that all we have to do is look at the discriminant, analyze the discriminant of the auxiliary equation, and that tells us the type of solution that we get to the original differential equation. So, as an example, suppose we have a spring mass system, and the differential equation that models the system is x double prime plus beta times x prime plus 10x equals 0. This is an example of free damped motion. Beta is the damping coefficient. Well, if beta is big enough, in other words, if the system is damped enough, we won't have any oscillations. But if beta is not big enough, we can have oscillations. So let's look at the three possible scenarios involving the discriminant. Let's call the discriminant of the auxiliary equation D. And it's very easy for us to jump right to that discriminant. It's beta squared minus 4 times 10, which is beta squared minus 40. Okay, now let's look at the three cases that we have up above. Same thing we did up above here. If D is less than 0, then the form of the solution is y equals e to the ax times c1 cosine dx oh, sorry. Our solution is supposed to be x, which is a function of t, so let's fix that. Our solution will have the form x equals e to the at times c1 cosine bt plus c2 sine bt. So we still have oscillations. This is called damped oscillation, damped oscillatory motion. And so what's going on here is that we haven't damped the system enough to prevent oscillations, which, if we don't have any damping at all, then we've got the oscillations involved in the harmonic motion. So we haven't damped it enough to get rid of the oscillations. So we call this the underdamped case. Now suppose D is exactly equal to 0. Well, then the type of solution that we get is the type that we have up above from having the repeated real roots. But more importantly, something to notice here is that this is a critical situation. We say that the system is critically damped because any decrease in the damping, no matter how slight, will put us back in the underdamped case and we'll have the oscillations. Now if you do write the solution and analyze the form of the solution, you'll see that you can pass through equilibrium at most once and have at most one turning point in this situation. Now suppose that D is greater than 0. Well, then we'll have two distinct real solutions. Not only that, but we'll have room to decrease the damping. If the decrease is slight enough, we won't go back to the underdamped case. So we call this the overdamped case. And the form of the solution that we get would be as given up above in the situation where we have two distinct real roots. And again, if you analyze the form, you'll see that you can pass through equilibrium at most once and have at most one turning point. So we see that we can analyze the discriminant of the auxiliary equation to find the types of solutions that we get to the second order linear homogeneous differential equation with constant coefficients without actually solving the equation.